Welcome everybody to the introduction to supercomputing at Ghent University, HPC UGent. First of all, I'm very sorry to keep you indoors during this type of weather. We'll see how long it takes during the hands-on this afternoon. It's up to you how long you stay. So if you want to enjoy the sun a bit, you'll get a chance to. We'll introduce you to the HPC infrastructure at Ghent University this morning with a lecture that will take about 2 hours. I think, actually, that's in the slides. Yeah, so that's the plan for today. In the morning, we'll do the presentation, including some Q&A. We'll then do a quick sandwich lunch. I hope the sandwiches show up. And at about 1, we'll do a guided tour of the data center, which is just across the parking lot here, so it's very close. That will also take about 1 hour. And then afterwards, we'll do a hands-on session where you can get started with using the HPC infrastructure. There's no guided exercises or something for the hands-on. It's really up to you how far you are along. Are you just getting started from zero? Do you already have some experience? Do you have hands-on questions or problems that you want to get some help with? So we will be here with 4 people from the HPC support team walking around and answering any questions you may have. And it's up to you how long you stay. You can stay until 5, but you can run out earlier as well. We will not be angry if you do that. Okay, to get started with, first of all, we have extensive documentation on using the HPC infrastructure as well. We will be covering some parts of that throughout the lecture today, but definitely not everything. There's way more detailed things in there that we will not cover today. But this is more or less an overview of the chapters or the sections that we will be covering. So everything we're talking about today here is essentially also covered in the documentation, although in a slightly different way, perhaps. There are some plans to revamp the documentation quite a bit in the coming weeks and months. So you may see this evolve quite a lot, actually, in the near future. To get started, let's first take a look at what HPC, what supercomputing, what scientific computing is all about, and what we do with the HPC UGent team. So we're part of the central IT department here at Ghent University, and we aim to help anyone who wants to use our infrastructure for doing scientific computing. That includes people here at Ghent University. It also includes other knowledge institutes in Flanders, including other Flemish universities, and also industries or companies who want to use scientific computing. This is the team. This is the backend team. So the people we usually hide in the basement, who make sure that everything keeps running nicely, everything is secure and up to date. So we now have 6 people doing that, essentially. And now, it used to be one big team. Now it's sort of split into 2 separate teams, a backend and a front-end team. This is the front-end team, the HPC support, with Ewald as the lead. And myself and Lara here, who are, let's say, second-line support. So we look into software installations, for example, and some of the more complex questions. And then Balázs and Elisa are doing first-line support. So that's typically the first contact that you have when you answer any questions through the support email address. Gottfried is helping us out with some user support and mostly documentation. And then we have a consultant in Czech Republic, Pavel, who's helping out a lot with software installations as well. All right, and I pass the word to Lara.
I hope everybody can hear me also in the Teams meeting. So what is high-performance computing? High-performance computing is running computations on a supercomputer. And a supercomputer is like, categorized because of the particular size that it has and its supported degree of parallelism, available memory and disk space available on there. We'll also mention computer clusters today, which is a group of servers of computers tightly or loosely knit together that can work together to do computations. We'll also use terms like supercomputing and scientific computing throughout the presentation today, but they all mainly mean the same thing. So what is high-performance computer? Here we see some pictures from high-performance computers, from the first digital computer Colossus to some DIY clusters in some basement here at the UGent, or fancy supercomputers like the one in Barcelona that was built on the university chapel with Mare Nostrum 4. What can you do with supercomputers? A lot of stuff. You can do weather prediction, animation rendering, all kinds of simulations like fluid dynamics or nuclear or atomic or nuclear simulations. Some more on the terminology that we'll be using today. For instance, worker nodes or clusters. Here on the picture, you can see a visualization of our default cluster, which is called Doduo. On there, you can see all the different worker nodes on it. So Doduo consists of 128 worker nodes, and each block in the diagram represents one worker node. And one worker node is the equivalent of one computer, even though it has a lot more cores and a lot more compute power than your average laptop or workstation has. If you want to check out how big the other clusters are and the specifics on them, like if they have GPUs or not, then you can check our documentation for information on the tier 2 clusters. Some more terminology. So here you can see a zoomed in of one worker node. So a worker node consists of 2 sockets most of the time with multiprocessors. Why are cores so important? Because the cores in the worker nodes are the things that actually do the calculations. So understanding how cores work and how calculations work helps you to know how you can run multi-core processes, make your software faster. Most software that is out there is sequential. Also, if you write like your own Python code, or you have some code somewhere, or a bash script is going to be sequential. So that means that you're only going to use one core for that calculation, and it will do all the steps in your code one by one on the single core. So if you have code like that and you ask for 100 cores on the cluster, you will wait for a long time, but it will actually not use all the available resources in your allocation, so it will still probably be slow. What you can do, however, is things that's called like embarrassingly parallel. So if you have a big data set and you want to do an analysis of like each data point in the data set, then you can actually send the different data sets to one core, so you can do multiple analysis at the same time and have your whole data set analyzed at the end much quicker. If your software is maybe parallel, then you can run your code a lot faster by parallelizing. You can split up the work, as I showed you with the embarrassing parallel. The challenge with parallelizing your code is that you have to try to keep your cores as busy as possible. So you have to start looking at bottlenecks maybe in your code, like when it's waiting for memory, so the cores are being idle while it's waiting for all the data that it needs to come to it. So stuff like that. So what is parallel software? If you're using a particular code and you find in their documentation that it's parallel or that there's OMP or MPI support, then your software is parallel. So asking for more cores will likely make it faster. So for instance, OpenPhone can easily go a lot faster with 160 cores. There are 2 main paradigms in parallel computing, OpenMP and MPI. OpenMP is when you're on one worker node and the code will send the different calculations in one single worker node. MPI and do the communication between the cores all in one worker node. If you want to have communication between different worker nodes, then you're going to have to use MPI. Also, for parallel computing, it's not because your code is parallel that you have to ask as much resources out there, because maybe your code doesn't scale anymore. So maybe it's like flat lines at like one node. So then it's not handy to ask for 3 or 4 because you're going to wait longer in the queue than you're making your code faster. yeah, you might now ask, like, how do we know how much we should ask for? And yeah, that's trial and error to see if you can get it a little bit quicker by asking more or not. So here you can see our data center, which we'll visit later today with the people here in the room. Yeah, and these are the different clusters that are here in our room. Yeah, for the people here, you can take pictures later today and stuff. So now I will leave it back to Kenneth.
You can not only take pictures, you can do a TikTok dance in front of the supercomputer as well. I keep making that challenge and nobody has done it, so you could be the first one to do it. So if we look at supercomputers on a bigger scale, let's say on the European scale, we usually use this picture here, this overview, where we have 4 different levels essentially. So the bottom level is tier 3. That's essentially your own laptop, your own computer. So you can already do some scientific calculations on your own computer, but small scale, maybe with a Jupyter notebook or something, analyzing some data. So that's already doable. Now, if you're doing bigger research, lots of data, heavy simulations, you may need to climb up the pyramid to bigger and bigger systems. On the tier 2 level, you're typically operating on an institute level, so a single university. So that's most of the systems that we will be seeing today here in the data center. That's the tier 2 clusters. A level above that is tier 1. That's already where money-wise, it's difficult for a single institution to operate a cluster of this size. So as you go up the pyramid, clusters get bigger and bigger, get more expensive, get more power hungry, and so on. We do have one tier 1 system in Flanders. Actually, the goal is to have one tier 1 system at any time in Flanders. Today, we actually have 2. There is one here in the data center in Ghent, tier 1 Hortense, that you can see up close. A second one is now being prepared in Brussels already, and it's very close to being operation ready. So in the next 2 years, more or less, we'll actually have 2 tier 1 systems in Flanders, an older one and a very new one. And we'll be seeing a bit more about that in the upcoming slides as well. And then as you climb up the pyramid, especially the top, going to tier 0, there you're talking really about European level systems where the EU is subsidizing a lot of the cost of the system to purchase it and to keep it running. There's about a dozen or so tier 0 systems in Europe. And the one in the picture that you see there is, or was the biggest one in Europe for a while, is in Finland. This is the Lumi system that you may have heard about. There is a bigger one now, the Jupyter system in Germany. And yeah, these things are essentially once a year or so, another system is added on a European level as well. Of course, things are different as you climb the pyramid. Things get bigger, things get more difficult to use. Access is also not free anymore at the top of the pyramid. So tier 0, tier 1 level, you have to do an application which is reviewed and approved, and then you get a certain amount of time to do the compute. So things get different as you climb up the pyramid. But from the tier 2 level onwards, it's more or less the same type of workflow that you follow when using these systems. So let's start at tier 2 here at Ghent University. What do we have today? We have 7 tier 2 clusters, tier 2 systems in operation, and one being prepared. So one new system that will become available very soon, which we call currently in pilot mode. So limited access, still under testing, and not fully stable yet. We'll see more details on each of these. There's three different groups, essentially: CPU-only compute clusters, GPU clusters, and then a special one, which we call an interactive debug cluster. And I'll explain what the difference is. What is important here, that you can get access to all this infrastructure for free, essentially. Everything is centrally funded through the Flemish Research Fund. So once you have your VSC account, you can log into this system and you can start using it. And there is no bill coming afterwards. Everything is already funded, is already paid for, essentially, including our time to provide the support. What is also important, and we'll get back to that, is that all of these clusters are running Linux as an operating system. So you have to be somewhat familiar with Linux to use them, at least in a good way. So let's start with the compute clusters. We have 3 in production, 1 being prepared in pilot. So as you go down the list, you essentially get newer and newer hardware. So our current default cluster Duo is now 4 or 5 years old, let's say. But you can see it's still very capable hardware. It has 128 nodes, so 128 computers connected together, with a fast network. And each of the nodes has 96 cores, so about 100 cores. Compared to your laptop has 4 cores. You can already see a big scale difference here with these systems, even within a single computer, within a single node. Each of these nodes also has 250 gigabytes of memory. Your laptop has maybe 16. So to give you an idea of the difference. And that's our oldest hardware. That's 4 or 5 years old. If you look into the other systems, that's typically newer hardware, or sometimes a little bit different hardware. So the Galate cluster here, the second one in the list, is a lot smaller, only has 16 nodes. But each of these nodes has close to 1 terabyte of memory. So not disk space, but memory for live data for running calculations. So that's way beyond what you can typically see even within high-end servers. And then these are just new generations that are essentially going to replace the dual cluster, which will be retired quite soon. So if you're going down the list, keep in mind things usually get better and faster. And that may be important to determine which cluster you will pick. All of these, other than the different CPUs, different generations, have high-speed network between all these nodes, fast access to the shared file systems. We'll get back to that. And all of them also have a fast local disk and an SSD where you can do very fast I/O type of workload. Does anyone know what the pictures are on the right? Yeah, they're all Pokemon. So all our clusters are named after a Pokemon. And it's a small game inside of the team. Each of the names has a meaning as well. So it's somehow connected to the hardware of the cluster. Like Galate has a lot of memory, and that Pokemon is very good at remembering things, for example. All right, the GPU cluster, same thing. Again, 3 more Pokemon, Joltik, Excelgor, and Litleo. And essentially the same type of thing here, new generation. So Joltik is our oldest one with the Volta GPUs, which are now, again, 5, maybe 6 years old. So quite old, but still more capable than what you typically find in your own workstation or laptop. And then as you go to Excelgor and Litleo, you get more of the high-end GPUs. The ones in Litleo, the Hopper ones, the H100 ones, have close to 100 gigabytes of GPU memory, next to 300 gigabytes of memory on the node itself. So if you're doing large language models, for example, this is already very attractive to use. Now, you can also see that things become smaller as we go down to the newer clusters. So we go from 10 nodes to 8 nodes. That's because things get way more expensive over time. So these Hopper nodes, or these Hopper GPUs, I usually say GPU is about the cost of a car. And it used to be a small car, now it's a very fancy car. So as things become newer and as AI steals all the GPUs, things become more expensive for us to get our hands on. Now, everything combined, this is still pretty okay to get access to for your research and essentially for free, right? So there's no cost here to access all this infrastructure. And then there's one special type of cluster, which we call an interactive debug cluster. This is a bit of a reaction to people complaining that they always have to wait in the queue, even for small things, for a session to start. So this is a bit of a reaction to that. It's essentially very old hardware, which was retired or went out of support for a long time ago, but we're still using it. And we're using it to allow people to get quick access to a handful or a small amount of resources without waiting in the queue. So on the interactive debug cluster, you can get access to 8 CPU cores and 27 gigabytes of memory, which is more or less equivalent to a laptop. But you're getting that resources on the CPU, on the HPC clusters, and you can play around, test your workloads there, test your job scripts, analyze some data as you would be on your own laptop, essentially. And this session, with these limits in mind, will always start without having to wait for hours or days until it starts. So it's a bit of a middle ground. It's not fast hardware, but you do get access instantly, and you can play around and test things quite easily. Yeah, there's a question already. Yeah. Pilot just means you can't access it yet. It's physically in the data center. It's operational. We can access it, and very soon we'll give, let's say, limited access to certain people who are well experienced to essentially stress test the system, let's say. And then in about 2 or 3 months or so, we'll open it up to everybody else, and it will become part of the pool. Yeah, that's what pilot mode means. So installing a new cluster means not only installing the hardware, but configuring all the systems, making sure it's all stable, the network is stable, installing all the software. And then we usually give a handful of people some early access to test it out. And as long as they don't report any serious problems, we just open it up to everybody and becomes part of the pool. Yeah. Good question. All right. So that was tier 2 at Ghent University. The other Flemish universities also have their own tier 2 infrastructure, which you can also access with your VSC account. So with the same account, you can log into Leuven, Brussels, Antwerp, and you can also access the resources there. So this is because we collaborate with the Flemish universities in the Flemish Supercomputing Center, which is not a physical center, but just a collaboration between the 4 biggest universities. You can access the resources there, but sometimes the usage model is a little bit different. At Ghent and Brussels, you can log into the system, submit jobs, they will start, and there's no bill coming afterwards. Antwerp and Leuven use a slightly different model. There they have a credit system where you need a certain amount of credits to be able to run compute jobs. I think to start with, they give you a small amount so you can test things out. But over time, as you do more bigger things, you will need to pay for your credits. It's a very small amount of money. It's just to force you to think what you're doing, essentially. And it's nowhere close to the full cost of what you're actually consuming. But it is a different model. That's not the case in Brussels, not the case in Ghent. And then we can climb up the pyramid as well and look at in tier 1. So the current production tier 1 compute cluster for the Flemish Supercomputing Center is called Hortense and is located here in Ghent. So you'll be able to see it. You won't see the Pokemon, but you will see the other part of the artwork. So this has been in operation since 2021. We are hosting the system. We are supporting the system. We are operating and maintaining the system as well. So this is a lot of work because this hardware is a lot bigger than you see on a tier 2 level. Everything combined here, Hortense has 100,000 CPU cores in total, compared to, well, do the math for the other ones, but it's a lot smaller in the tier 2 clusters. And this also has 40 GPU nodes, where each of them has four A100 GPUs. So there's 160 GPUs in this system alone. So it's a bigger scale than the tier 2 systems, even though it's already about 5 years old. High-speed network, again, lots of storage, so 6 petabytes, 6,000 terabytes of dedicated storage on this system. And the access model here is a little bit different. So here you need to propose a project, which is then reviewed. There's 3 cutoff dates, so 3 deadlines is, let's say, where you can propose a project. It's reviewed and then hopefully accepted. If it is accepted, you get a certain amount of time. I think it's about 8 months, where you can spend the compute resources that you proposed to use for a particular research topic. Now, the good news is once your project is approved, there's, again, no bill coming afterwards. Everything is already paid for, but there is a step, let's say, to getting access to this type of hardware. The same applies to the other tier 1 systems in Flanders. The same applies to the tier 0 systems on the European level as well, where they have a similar type of access model. I should say the access is free for academics. On tier 1, industry can also get access to tier 1, but they pay for what they use. So there, the access is, of course, not free for companies. And like I said, the goal is to always have a tier 1 system in Flanders. The current one is getting rather old, and frankly, a bit annoying to still operate as well, but we'll run it for as long as we can. The next one is already being prepared in Brussels. It's physically there. It's already been inaugurated. It's an investment of 8 million euros. So you can imagine the amount of money that goes into this thing and why this could be too big for a single university to carry. So that's why it's a collaboration. At first sight, this looks smaller in terms of hardware. This only has 25,000 CPU cores. Hortense has 100,000. The big reason for this is that the hardware has sort of shifted more towards GPUs than it has before. So currently, Sophia already has over 160 of the very latest GPUs. And this is just phase 1 of the system. There's a phase 2 most likely coming as well. So the number of GPUs will only go up. And again, these GPUs are way more expensive than what we've seen in the past with the ones in Hortense. Same issue, same aspect again, fast network between all these nodes and all these GPUs. Some dedicated visualization nodes to do some high detail visualization work, interactive work. Lots of storage available. So 4 petabytes of scratch storage and then 24 terabytes of very fast NVMe storage as well. This thing looks pretty cool. So you can see there the head of the IT team, of the HPC team rather, at the VUB, Wart, is in the picture for scale. So you can have an idea of how big it is. The data center that it's housed in is on the bottom left, but the supercomputer only takes a very small room in this data center. So don't imagine that the whole thing is filled with the supercomputer. That's definitely not the case. The Flemish government is not rich enough to fill a building like this. On the right, you can see some of the basement facilities, let's say, that are necessary to run a data center like this. So lots of piping work for the cooling and all of this stuff. And it's very nice that you can see the people in there because you really get a sense of the scale of how big things are. You will see similar things here in the data center as well. Okay, then another aspect of the tier 1 infrastructure at the VSC is our own private cloud. So a bit similar to what you have in Azure or Amazon, where you can get virtual machines that you manage yourself and you just pay them big bucks to get access to those resources. You can get access to virtual machines at the VSC as well, again, free of charge. And you manage things yourself. So if you want to, you can install Windows on there and you fully operate your own software environment. Of course, it has to be for research purposes. So here, there's also a project that you need to propose, and you essentially need to explain what you're going to do and what you're going to use these resources for. And then you get access with some documentation, and it's up to you how you manage this. So just keep this in mind. If you have a need for, let's say, a public web interface to give access to your data, this is one of the things you can explore. All right, Lara, back to you.
Yes. So how can you get getting a VSC account? I hope everybody in the room already has a VSC account because you really need it for the afternoon session. So anybody as a member of the UGent Association can get a VSC account. That includes researchers, staff, but also master and bachelor students. So you can also use it in courses with your students. Yeah, it can be used to access all the VSC sites in Flanders. You will be subscribed to the HPC Announce and the HPC Users. To the HPC Announce, you can unsubscribe if you want to, but if you want to unsubscribe from the other one as well, you have to deactivate your account. If you're using it for exams or teaching, be aware that we cannot guarantee that the HPC is always there. So always have a backup plan. Try to work with a project work so that the students have multiple weeks to accomplish it, so that they're not being hindered if the system might be out for some time. You can also see our documentation for more information on all these things. How do you manage your VSC account? So if you want to add an SSH key or get more data, join a group or create a VO or join a VO, that you all do via account.vscentrum.be. And there you can also find all the information on your account. So you can also check there if if your storage is almost full and stuff like that. So what is the general workflow on an HPC infrastructure? First, you log into the login nodes, you transfer the files or create new files or get your code on the system. Then you compile and test your code preferably on our debug cluster and not on our login nodes. You create a job script, you submit the job, and then you're patient and wait until your job is out of the queue, it gets executed and is complete. And once your job is completed, you can inspect your results. So this is a high-level overview of the UGent infrastructure. So we have two ways of getting access to the login nodes. You can do it via SSH in a terminal, or you can use our web portal. So if you're not used to using a command line and figuring out the SSH key, it's best, we prefer that you use our portal. Very likely, if you send an email with I can't log in via SSH, we will probably tell you, please use the portal. So you're a little bit on your own if you want to log in via SSH key. We will try to help, but probably not our best effort. So if once you're logged in, you're either logged in on a Gleiger 09 or Gleiger 10, which are our login nodes. And from there, you have access to the file system and also to the compute nodes. So that is a place where you submit jobs to, transfer files, manage your file system. So if you're doing cleanup or stuff like that. So first way to connect to the H via SSH is to login.hpc.be, and then you get logged in with the terminal. You can also do it on Windows, but then you have to use PuTTY, which can be a little bit of a mess. Via Linux and Mac OS, you can do it via SSH. But yeah, we prefer that you use the web portal. We have a dedicated section on the web portal in our documentation. You can run it on any standard internet browser, Firefox, Chrome, even your phone. You do not need an SSH key, and you could do anything. You can have a shell session, a desktop environment, or an interactive app. You can also just have a terminal in the web portal, so you can just open the terminal to the login nodes, and if you're familiar with Linux, do anything that you want there. You can also use it to manage your files in the file system. You can check the different storage that is available and what is in there for you. You can create new files, move files. You can even upload files if they're not too big. Download files, so you can do anything. Then we also have interactive apps in the web portal. So if you're used to using a Jupyter Notebook or RStudio Server on your laptop, you can also just do this on the supercomputer. Here is a step-by-step plan of how you start a Jupyter Notebook on our system. So you first specify the cluster which you want to run on. In this case, it's going for Donphan, our debug cluster. You ask for the number of hours you want to run, the number of nodes you want, the number of cores. One thing you do have to be careful for is that if you want, for instance, to use PyTorch in your Jupyter environment, you have to make sure that the Jupyter version and the PyTorch version are the same. So that's because otherwise it will be broken. Yes, and so once you're done, you can submit, you wait in the queue, and then it's starting, and then you will see the familiar interface if you're used to using Jupyter. You can also have an interactive desktop on the Jupyter Notebook on the portal. So, for instance, to run MATLAB, so you go through the same steps as you went through for a Jupyter Notebook to start it, and then you can open a terminal and start MATLAB, and then you will get the MATLAB interface in the desktop. If you're going to the web portal, you might land on this page which will say you need to connect to the firewall app. If you land on that, you click on the firewall app. It will ask you to sign in and ask to authorize that the firewall, HPC firewall, can be used. It will open the following browser. Please don't close that browser, because if you close it again, you will lose connection again to the web portal. But if you keep it running on the background, you can do anything. If you're on the university network, then you will you won't see this. But if you're working from home or outside of Belgium or Europe, you will likely have to use the firewall app. As I mentioned, all the operating systems on our clusters are Linux. So if you want to have the full power and of using the supercomputer and really use all the everything that is possible on there, we really recommend that you learn the Linux command interface and the Linux shell environment. We have some common commands here in the slides, like change directory and list files and create directories. Yeah, it can be a very powerful tool because Linux commands can also be piped. So so it might seem very archaic, but it's very powerful. It's also the same scripting language as you use as Bash. So you use it in job scripts. We also have a dedicated section on the on Linux in our documentation with a Linux tutorial if you want to learn more. And then I will leave it back to Kenneth.
Before we continue, let's maybe do a quick demo of that web portal to make it a bit more concrete. So once you log into the web portal, you'll be seeing a page like this. Like Lara mentioned, you can go through all the directories that you have access to here. There's a lot of them. I will explain the differences in a bit in one of the upcoming slides. Suppose, say I go to my data VO directory here. You'll see a file listing. You can click open any of the directories here, see what is there. If you have any files, you can inspect the content of the files. Let me show you one of them. You can view, it's actually downloading the file, okay. Yeah, you can view a file, you can edit a file. So this is just an interactive browser where you can make editor rather, where you can make changes and save them. You can download files, you can copy files around, move them around, and so on. So this is quite intuitive to use, and perhaps easier to use than a Linux shell environment, which you can also get. You can either click here to get shell access to a login node. So you'll see the terminal window that Lara mentioned. Also from the file browser, you can say this particular directory where I'm in, I want to open this in a terminal, and it will jump straight to there. And from here, you can start using Linux commands like ls, editors, creating directories, removing files, and so on. So that's one part. Another part, and maybe more interesting part, is the interactive apps, where you can, for example, start a Jupyter notebook. Let me see before I try this, if I actually have a session running on Donphan. I'll get back to the module swap and all this shenanigans in a bit. Yes, I do have a session here, so I'm going to cancel this one. Right. So I just want to quickly show you starting a Jupyter notebook means you first pick a cluster. So which of the clusters do you want to use? Let's go for the interactive cluster so we don't have to wait in the queue. On the interactive cluster, you get a limit of maximum 8 cores. So let's say we need 4 cores here. That gives us 13 gigabytes of memory. We pick a Jupyter notebook version. As Lara mentioned, here you may need to be a bit careful, especially if you want to add additional software next to the notebook itself. So say you want PyTorch available in your notebook, you can do this by doing extra module load commands in here. I'll explain a bit more on that, but they have to be compatible with the notebook version you are using. So that's coming up. But let's assume everything is okay here. I click launch. And initially, you'll see that your session is waiting in the queue. So it's waiting for resources to become available, in this case, 4 cores. Because we are using the Donphan cluster, this should start straight away. So you can see it already goes to starting. And it will auto refresh when the session is actually running. And you'll get a button here that allows you to connect to it. One thing I didn't do is change the amount of time requested for the session. I left it to the default of 1 hour. So that's all the time I get. After 1 hour, the session will be stopped automatically. You can change this up to 72 hours, 3 days maximum. Beyond that, you'll have to do things in separate jobs. So it should auto refresh and give me a button. Here it goes. You get a connect button. And if you click that button, it will drop you in a Jupyter notebook environment, and you can start accessing files, doing data analysis, maybe running some small calculations and so on. So it's still starting, but it should fall through eventually. Now, what's also nice is if you're doing this on a train, for example, you'll probably lose connection at some point. You can later just reconnect to the sessions that we're running. So if let's say I start a new notebook here, like this, All right, and I just start working, and then I lose my connection. Right, so I execute the import, all my tabs die. Yes, I can leave. Also here, all of this dies. Ignore the wall of text here, that's a weird issue. If you later log in again, you can just reconnect to that notebook, and you should be seeing the same type of environment. So hopefully that notebook I had running before is still running here, and I can just go back to it and continue the way I was doing before. Not sure why the import isn't there, maybe it didn't finish. But you can reconnect to the same session that you have. Also interesting is the desktop environment. So here, if I start this with another 4 cores, it should also still start, because in total, I'm still only using 8 cores on Donphan. Here, I'll just click launch. And this will create a Linux desktop environment on one of the worker nodes on the cluster, where you can easily connect to straight from your browser without installing any software. You can get a desktop environment like you have on your laptop, but running on the clusters. And you can start software there, play around, and work interactively. So this is a very nice environment, quite similar to the Jupyter Notebook. So here I can right click, start the terminal, load modules to activate software, and for example, start MATLAB. Check that. So this is, I want to say, sort of new. We've now had it for, I think, 5-6 years already. But this lowers the bar to using the HPC infrastructure quite a bit compared to only having SSH access and only the Linux terminal. This changes things quite a bit. All right. Any questions on that before we continue? Yes. Okay. Yeah. Good question. So essentially, is there a backup of the data that you upload into your account? The short answer is no. So you're responsible for backing up any important data outside of the system yourself. So that's a good question. We used to have backups before, but it was too expensive to maintain. Essentially, we have petabytes of data. We have to back it all up. And what we see happening is that many people don't clean up their stuff. So we're actually backing up a lot, and maybe 1% of that is actually useful data. So you have to make sure that whatever is important data files, important results, job scripts that you don't want to lose, that you back up those yourself locally. There's a couple of options there. You can, if they're small enough, you can just download them to your laptop. There's also a connection possible to the UGent shares, for example, straight from the HPC cluster. You can just copy data back and forth between the shares, and you can use that as a sort of backup option. Now, again, it depends a lot on the volume of data that we're talking. If you're talking terabytes, then it gets interesting. If you have a use case like this where you're literally talking terabytes, maybe send us an email, hpc@ugent.be, and we can give you some guidance on how to deal with that. Good question. Any others before we continue? Yeah. 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 Can data be deleted directly because it's too much?
Yeah, because users are running and
Yeah.
the data file is getting saved.
Yeah.
500.
So we will not delete data for you automatically. What will happen is you have a certain amount of disk space available. I'll get to that. By default, it's 25 gigabytes, but you can get terabytes if you want to. If your disk space is full, it stops and everything will stop crashing because it cannot write any more data. But we will not clean up data for you. So you have to either do this yourself manually or come up with some kind of automated way of moving data around or cleaning data up yourself. Yeah, if the simulation is running, as long as you have disk space available, it can keep writing data. If your disk space is full, the simulation will crash. And you will see in your job output files that things are this quota exceeded or whatever. Yes. Yeah. You can have hundreds of jobs running at the same time while you download data interactively. That all works. Yeah, no problem. Okay, but this will become a bit more clear, I think, when we get to the disk space section. Yeah. Yeah. Oh, is it?
No, mine is not on.
No, mine is on, I think. Oh, no, here. It shouldn't be down there. That's why. Yeah. Okay. There may be more questions, but I think I'll cover some of them in the upcoming slides. So, all right. So imagine you have figured out how to connect to the system, web portal, SSH. One of the next things that you want to do is do actual real calculations. So rather than working interactively, which can be very useful, but if you're doing lots of calculations, hundreds, maybe thousands of things, or even tens is already problematic to do interactively, you definitely want to work with jobs. So jobs are essentially scripts that you submit to the system. The system figures out where to run them and when they can start, when the resources are available. And in the end, you'll get results, data files, numbers, depending on what your simulation or what your workload is doing. The way this is done is you use these shell commands like qsub to submit a job, qdel to delete a job, qstat to check how your jobs are doing, and so on. So we'll do some hands-on examples of basic things. I definitely recommend that you try some of this out with some of the basic examples that we'll give you, so you're familiar with how this works. Because it is a bit weird if you've never used this before, but it's always the same thing again and again, no matter how complex the jobs that you're running really are. So getting the basics of this can be very useful. So let's look at some of the, let's say, more general information first. What is a job script? So a job script is a text file, essentially, that is written in shell commands. So the stuff that you run directly in a Linux terminal is exactly the same stuff that you use in a job script as well. A very minimal job script is on the top right there. The first line just says it's a bash script. So it has a hash bang bin bash that just tells the system what type of script it is. And then there's an echo command that just prints a line that says, hello, I'm a job script. This is the most minimal job script that you can run, essentially. That's a general shell script. What makes the shell script a job script is essentially three things. There's one part at the top where you specify the resources that you need, how many cores, how much time, maybe GPUs, maybe extra memory, and so on. Then there's a part where you prepare the software environment to use. So do you want to use MATLAB or or PyTorch or something else, R? So there's a way to explain that to the system via module load commands, for example. And then the actual work is usually preparing input files or finding the input files, running the actual workload. So that's where most time is spent, of course, usually. And then maybe copying back some results to make sure you don't lose them. So that's really the high-level overview of a job script. And we'll see concrete examples of that in a bit. So starting with the first part, the top part, required resources. Here's a concrete example. With these hash PBS lines, we tell the system information about our job, high-level information. We can give it a name. We can ask for a certain number of cores and nodes. So the second PBS line says nodes equals 1, colon, ppn equals 4. So ppn stands for processors per node, which is wrong. It should be cores per node, but this system is old enough that processors only had 1 core back then. So that's why it says ppn. So we're asking for 4 cores here to be available to this job. The third PBS line says, I want 10 hours of time for this. So after 10 hours, this job will be stopped no matter what. If it finishes before 10 hours, that's fine. Right? So maybe you don't know how long things will run, and that's OK. And the fourth line is asking for 50 gigabytes of memory. You should only use that when the default amount of memory that you get is not sufficient. The default that you get is based on the number of cores that you ask. So there's maybe, on average, 4 gigabytes per core available on that system, on that cluster. So 4 times 4 is 16 gigabytes is what you will get by default. Maybe the software that you're running needs more and you see errors because of a lack of memory, then you can just ask for more memory in your job script. So that's all the resource requests that you see typically at the top of a job script. What's important here, yeah, I'll get back to the question in a bit. What's important here, there is a hard limit on the wall time, 72 hours. If you ask for more, the job will just not work. You will not be able to submit it, or it will never start. It's fine if you ask for more and your job finishes earlier, that's fine. the reverse is not possible. So if your job keeps running, it will be stopped after the amount of time has expired. Now, a question that we typically get is, how much time should I ask for? Well, it depends. Depends which cluster you're using, depends which software you're using, depends how much data you're reading in or what the parameters of the simulation are. So it's really trial and error is the best answer we can give there. Now, it is in your best interest to not always ask for 72 hours because the amount of cores, the amount of nodes, the amount of wall time, and the amount of memory that you use are all factored in to determine which job gets to start next. So the more you ask for, typically, the longer you will have to wait. So shortening the time is in your interest, but making it too short and making your job crash in the end or be killed in the end is not interesting either. So it's a bit of a balance there. Initially, just start with the max 72 hours, especially if you're on Donfon, it doesn't actually matter because your job will start straight anyway. But over time, you should get the hang of things and realize how long things take and then maybe limit this a bit. Yes, question? Yeah, that's a very technical difference. On some systems, so memory means the actual amount of RAM memory that is available in the computer. Virtual memory can mean more than that because there could be amount of swap memory in the system as well. So swap is where if you fill up your memory, it uses the swap memory and it starts saving things to disk and restoring them all again and again into memory, from disk to memory and the other way around. That's very, very slow. So if you exceed the amount of available memory, things will get horribly slow. So typically on our systems, the swap is very minimal to almost no existent. So virtual memory and regular memory are pretty much the same thing on our systems. It doesn't really matter in practice, no. If you use mem equals 50 or vmem equals 50, it's pretty much the same thing. And really, if you're at that limit where you need virtual memory rather than memory, then things are too tight already, and you need to either use another cluster with more memory or scale down your workload a bit, because then you're already in the danger zone, let's say, of being killed. So same thing here. If you ask for 50 gigabytes of memory, as soon as you go 1 megabyte over, the system will kill your job and say, this is not what you got access to, so it stops for you here. Yeah, so you'll get the same type of problem. It used to be a bigger difference. Now it really doesn't matter. At least on our systems, it doesn't matter. Yeah, that's what I said. Yeah, there's really no difference anymore. Okay. Okay, so that's the first part of the job script. The second part is then the software part. So what software is available for doing our calculation? For this, we use the module system, the typical module system that you see on supercomputers. So we didn't invent this, and this is really used basically on any supercomputer in the world. There's a lot of details here, but what it really boils down to is that you're loading modules to activate software. And the best way to explain this is actually with a quick demo. So the module command is the central command here to activate the software. With module avail, you can check which software which is there. With module load, you then activate some of that software by loading those modules. With module list, which was on the previous slide, I think. Yeah, there at the bottom. With module list, you can check what is already loaded. With purge, you can start afresh, remove everything again. And then there's some details on which modules you can actually combine. Now, the best way to show this is, again, with a quick demo. So I'll open up a terminal session here in the browser and make it big enough. So the module command is what you're... Oh, this is hard to see. I'll just make it bigger. The module command is what you're working with. So module avail allows you to search for available software. So say I'm looking for GROMACS. I can do a module avail GROMACS. And the system will tell me which versions of GROMACS are available. You can see 3 modules here, GROMACS 24.4, 2 variants of that, one with plumed, one without, and then a weird one with constant pH, whatever this is about. So you can essentially pick one here and load it, and then GROMACS will be ready to use, essentially. Now let me use the SciPy bundle example. So these modules, you have a bunch of versions of these as well. Each of these activates a couple of Python modules like pandas, numpy, scipy. The way you can tell this is by using a module show. So let me do that again. I can copy one of them like this. And now with module show, you can actually inspect this module without loading it. You can see what's in there. This will print out a lot of text, but essentially it will tell you that this module has a bunch of extensions, including numpy, pandas, scipy, and specific versions of that. Now, the way you can tell is if you're looking for numpy, for example, the system will tell you that, okay, there are some things that have numpy in the name, but there's numpy itself as well, which is an extension. And it says to get more information about an extension, you do module spider, numpy. This will tell you numpy is, there's first of all different versions of numpy, so let's pick one. And it tells you to do module spider on that. So if you see text, read the text, and it's trying to help you really. And now it tells us that numpy version 2.3.2 is available in this scipy bundle module. So by loading this module, numpy will become available. Okay, to show this, module list says we only have a cluster module loaded. So which cluster are we talking to? If we try Python now, it's a pretty old version. If we try importing numpy, this will fail because numpy is not installed in this Python version. But thanks to the module system, we know that there is a way to activate another numpy or activate software where numpy is available. If you do module load scipy bundle, this will not generate any output, but it will do stuff in the background for you. If we now try checking the Python version, it's a lot newer. We have a Python 3.13. And if we try the import again, now it will work. So now numpy is actually available in this environment by some magic happening when the module was loaded. So keep this in mind. There's lots of software, thousands of packages. If you factor in R packages and Python packages that we have installed, it's probably over 5,000 things that we have installed, unique software without versions. So lots of things already available. It's very likely that the software that you need is already there. There may be old versions of things. If you're unhappy with versions, you can ask us to install a newer version. If software is entirely missing, you can also ask us to install it for you so you don't have to figure things out. And I'll get back to that in a bit. But that's let's say, the quick demo of working with the module system. Module avail to search, module load to activate software, module list to check what is loaded. So I loaded scipy bundle, but it activates a whole bunch of other things as well. And then module spider to help searching with extensions. Yeah, question? Yeah. We'll get to that in a bit. There are other ways that you can use the requirements file as well. Yeah. It is always recommended to try and use the central installations, but you'll have to explore a bit to understand where things are. Now, if you have a requirements file, you have a bunch of Python packages listed in there. That's probably not only NumPy, but a whole bunch of other things. If you load, let's say, a scipy bundle module, you can check with pip list what it already provides. And this will already be a pretty long list. It's not that you're only getting NumPy, you're getting a whole bunch of other things as well. So this takes a while while it figures. On the login notes, this can be quite slow. But if you do it in an interactive job on Donphan, for example, this will be a bit quicker. But you can see these are all Python packages that are already available out of the box beyond what's available in the standard Python. So yeah, this will be a bit of an exercise, but we have another way of dealing with that as well. You can essentially mix modules with the requirements file and only install the things that are missing. So we'll get back to that. Good question. All right. Was this helpful? This is very quick. Again, this is also something quite important in the system that you should try yourself hands-on and try to understand how this works. And first of all, if the software that you need is already there. And also on this, you can definitely ask questions during the hands-on this afternoon. All right, so this is the same thing, essentially, like I showed hands-on. By default, you get an old Python that doesn't have a lot of things that you may be interested in. By loading modules, you can activate a newer Python that has lots of additional Python packages available. Then this is a bit of extra detail, but in a Linux shell environment, you can play with environment variables as well, very close to what variables are in other programming languages. The two key ones, the two most important ones are on the top. So a $PBS job ID gives you the job ID of that job that is running. So this will be a unique number in the job that you can use to create output files and prevent that jobs overwrite each other's output files. And we'll use this in the examples. And the second one is PBS O workdir, so original working directory. This is the location from which your job was submitted. So if you do a QSub with a job script, the system essentially remembers that location, and you can use that location in the job script itself. And we will also use this. You will see this coming back. So it will probably click then when you see the example. The other ones are more detailed and maybe not that interesting. And then, of course, we also need input data. We're probably going to generate output data as well in our calculation. So where do we find it? Where can it be? Where can we store things? So like you already showed in the, or already saw in the portal, there's many different locations that you can get access to. There's essentially three big groups of directories. There's your home directory, the entry point to the system, which is only for a small amount of data, typically a handful of small files like job scripts or things like this. There's the data file system, which is for long-term storage of data. So big data sets that you want to analyze over and over again that you'll be using maybe for years on the system, you can put them there. Typically large files. And then there's the scratch file system. We actually have two scratch file systems today, a regular one and a fast one with SSDs. This is more for the live input data of the jobs. So this is a lot faster than the data file system. So it's interesting to put data there, especially if you're talking hundreds of gigabytes or terabytes of data that you want to analyze again and again in jobs. You may want to put it there so it's fast to access. The data file system is called long-term storage because we have a bit more protection on a hardware level to make sure we don't lose any data. We essentially have two copies of everything on two different hard drives. So if one hard drive dies, or if many hard drives die, we will likely not lose your data. On Scratch, we don't really do this, but to date, we've never lost any data files on the system since we've been operational since 2008, I think. That doesn't mean you shouldn't take backups, right? You should still take backups because it's not an if case, it's a when case. Sooner or later, there will be some big issue that may lead us to lose some data. So just take this into account. You can see the sizes of the different data of the different file systems there. So the data file system is 5.5 petabytes in hard drive space. But because we have two copies of everything, you have to divide that by 2 in terms of actual disk space. The Scratch file system is 2.6 petabytes in total. And then the other ones are a lot smaller. That's big, but as an individual user to start with, you only get a pretty limited amount of disk space. Your home directory is limited to 3 gigabytes. Your data and Scratch directory are limited to 25 gigabytes. That is quite small, but we have over 5,000 active accounts. So if you do this times 5,000, you can already see the numbers becoming quite big. Initially, that's good to start with, hopefully. If it is not good enough anymore, you can get access to a lot more disk space quite easily. The only thing you need to do is organize yourself or join what's called a virtual organization, which typically corresponds to a research group where you may be sharing data with your colleagues. And there you can get hundreds of gigabytes or even terabytes, essentially by just asking us. You can submit a request to get access to more disk space. You add 3 lines in there that explains why you need that disk space. And we usually click approve and say, it's OK. And half an hour later, that disk space is available for your account. So again, no cost, nothing too special, but it's a bit of a limit that we impose to make sure the whole thing stays manageable and that people don't accidentally generate terabytes of data and kill the whole system for everybody else. Also, this is well covered in the documentation how to do this and make this type of request. Just keep this in mind. Don't be stuck to the 25 gigabytes. You can definitely go beyond that quite easily. To check how you're doing in your account, how full it is in terms of disk space, you can use the account page, account.vscentrum.be. You have a personal tab there that shows the directories that you have access to. If you're in a virtual organization, a VO, You can also see how things are in the VO, generally speaking, so how much disk space is available for the entire VO for you and your colleagues, typically in the research group. And if you're a VO admin, you can see more detailed information as well in terms of which members are consuming the most disk space. And you can actually attach names to that as well, which are removed in the slide here. So for all, let's say, high-level overview of how things are looking currently, you can use the account page. All right. We're almost getting ready for a complete job script example. So there is one more thing, the actual workload that we want to run. I have two short examples here of calculations, which is a big word for these things, that use multiple cores. So it goes back to what Lara was saying about parallel computing. Typically on a supercomputer, you want to use multiple cores or maybe even multiple nodes and go really big for your calculations. This shows you a bit of C code that you don't need to fully understand, but it just gives you an idea of what things may look like inside of the software that you're using. So this is an OpenMP program that does multi-threading to use multiple cores. And in this case, it will just say hello from each of the cores. So not really a calculation, but close enough. So you use this C code, you put it in a file called example openmp.c. And in your job script, you would be compiling this C program into a binary, and that's just running the binary. Or you can do the compilation up front and just use the same binary again and again. If you're looking for an exercise to get started with, this is a good one. You can try to get this thing to run in, say, 4-8 cores on Donphan. Figure out how to write a job script to actually run this thing. We do have concrete examples of job scripts coming up. This is multi-threading. If you're doing distributed computing, so MPI, it looks a bit similar in terms of the C code. Again, you don't really need to understand it, but also here, you'll essentially be starting multiple copies of this same program. They will start talking to each other and do something useful. In this case, again, they will just say, hello, I'm number 1 out of 8 or whatever. And to run this, it's quite similar. You compile the C program into a binary, and you run the binary. Running MPI workloads needs this kind of prefix MPI run to tell it how many times it needs to start the same thing so they can start talking to each other. We have another tool called my MPI run, which makes this a bit easier. Because if you're submitting a job script that's asking for 4 cores, why do you again need to tell the system how many cores you want to use? It already knows. That's what my MPI run does for you. So you just do my MPI run, and it uses everything that's available in your job. This looks very scary, but the job script hopefully looks a bit less scary. So this is a full example of a job script. You can copy paste this into a text file, put it in your VSE account, and try running qsub on it. And it should be doing something useful under one important condition. So to go through it, top to bottom, the first line says bin bash. It is a bash shell script, so just always put this in your job scripts. We're asking for 1 core on 1 node and 2 hours of wall time to complete this job, which is going to be way too much. This will finish in seconds. The green line says we want to load a particular module that gives us Python 3.13 with some extra Python packages. The orange line, the CP line, says we are copying an input file from the location from which this job was submitted. So that's the PBS or workdir environment variable. And we're copying this to another location called tempdir. So tempdir is a unique directory that is created for each job on the local disk of the node where the job is running. We're doing this because potentially this input file could be big. It could be hundreds of gigabytes. We don't know this upfront. And we just want to make sure we can access this very quickly. The black line then does a CD to the tempdir. It does a change directory. So we're in the directory where this input file is located. And then with the pink line, we run a small Python program that reads the file, counts how many characters are in there, and prints that to the screen. And it doesn't actually go to the screen. We capture that output, and we put it in a file called output.txt with output redirection. That's what the arrow is doing at the end. That's all good. We have an output.txt file and the tempdir. If we now stop the job here, we will actually never see the results because the output file is in a temporary directory, which is automatically removed when the job script finishes. So that's why we need the extra step at the end. We need to copy the output file to a location where it will not be automatically removed. So we copy it, in this case, to our VSC data directory. And while we copy, we also add the job ID to the name of the file. So if you run the script again and again, we will get unique output files for each job. Now, there's one important condition here to run this job correctly. Does somebody see? So if you copy this in your Balazs, you know the answer. If you copy this in a text file, you do a QSub in your account, there will be a problem if that's the only thing that you do. Can somebody see the problem? You're not giving memory requirements. That's good. By default, you will get an amount of memory connected to the number of cores that you ask. So here you'll probably get 4 GB of memory, which should be enough to count characters in a file. So that's not the issue. You don't have to change anything to the job script itself, but there's something else that you need to do. And this is a very good example to start with, by the way. If you've never submitted a job script, try this first. Yeah. No, actually, no. If you do QSub, the system will do that for you. It doesn't need to be executable. That's a good thing. The one thing you need to do is you need to create that input file. Because if that input file doesn't exist, it will try to copy it. It will not find it. That will fail. It will go to a directory. The Python command will try to read the input file, which is not going to be there. So you'll get errors, and you won't get a useful result. So next to your job script, you need an input.txt file as well. Otherwise, you'll get errors. So what I recommend you to try is put this in the job script, do QSub without creating an input file, see how it fails, then create the input file next to it, submit again, and see how it works. That's a very good first experience. So this is a full, quite simple job script, single core, doesn't do a lot. Yeah, sorry. Yeah. So the VSC data environment variable has the path to your data directory inside. Yes, the directory exists. Yeah, so this is predefined. As soon as you log into the system, VSC data is always defined. So if I go in here and I print the contents of VSC data with an echo command, you will see this is a path specific to my account. That's not a weird question. It's, yeah, where does this come from? Because it's usually not there, but we predefine lots of things for you to make it easier. Okay, so this is a complete job script that you can literally copy paste, create an input file, and it should work in your account. So very good first experience. Let's look at a multi-node MPI job script or something big, right? And you'll see it's pretty much the same type of structure. So it's not certainly looking way more scary because you're doing bigger things. The main difference is that here at the top, we're asking for 2 nodes, 4 cores each, so 8 cores in total. So you can run this example still on Donphan. So it doesn't use more than 8 cores in total. The module loads are a bit different. We're loading a different module because we want to run an MPI workload. So we're loading an open MPI module. That's a particular implementation of the MPI library. You can also load what we call a full tool chain. So module load FOSS and this number instead, which is pretty much the same thing. It just activates more software. But in this case, you're not actually going to use it. And then we have a second module load that activates our My MPI run tool, which helps you to run MPI workloads. Then here, the same CD, there's no copying here. We just move to the location where this job was submitted from, because we expect to find the MPI hello.c source code here. We do the compilation command to transform this into a binary, and then we use My MPI run to run the binary. So again, same thing, resource request, activating software, actual workload. And in this case, there's not a lot of copying going on, input, output data, we don't need to. Now, so this is the MPI hello thing will generate output. Where is this output going to go? There's no screen. So what's going to happen with the output? What would make sense? Yeah, close, yes. So the output will go into the directory where your job was submitted from. In this case, it's the same one that you're changing to. That's actually the next slide, I think. So job output files. Oh, yes, sorry. Good question, because it's a stupid example. Yeah. You could just ask for 8 cores into a single node. That's what, yeah, that would make more sense. But just by means of example, that's, yeah. Well, you would only ask for multiple nodes if there's not enough cores in a single node to run your workload fast enough. In this case, it's gamed, so it still runs on Donphan. So that's why we're not asking for more than 8 cores. But that's a good question, yeah. You would use 8 cores in a single node instead, yeah. Yeah. Mm-hmm. Yes. Yeah, other jobs and potentially other people. Yeah. So if you ask for 8 cores and there's 100 cores available, the other 92 will be available to other jobs to run. Maybe your own jobs or maybe jobs from other people. Yeah. So you only get access to what you're asking for. Everything else is available to other people. Yeah. All right. So yeah, job output files. Long story short, essentially this means for every job you submit, there will be an output file generated. And by default, actually 2 output files. A .o file, which has the normal output, a .e file, which has the errors and the warnings. And again, this is something you will see when you do the simple example. Without creating the input.txt file, you'll do a qsub, you'll get 2 output files. The .o file will be empty, the .e file will have stuff in there, and usually having a non-empty .e file means there's trouble, something went wrong. You can join these together as well. You can tell the system to just create 1 output file for each job if that's what you prefer. And next to the standard output files, your software or your job script can also create additional output files, of course, depending on what it's doing. So if you're capturing output and error yourself, like the example here, you will also get these additional log files next to the general output files. Again, this is mostly getting used to how the system works. So try this hands-on and see what happens. And then this is the complete workflow. So if we have a job script called example.sh, we first tell the system to which cluster we want to submit it to. So we do a module swap, cluster Donphan, for example. And then we use the qsub command to submit the job script. We will get a job number back, 1, 2, 3, 4, 5 in this case. And then with qstat, we can see how that job is doing. So we ran qstat here, we get a job number, and we see it has been running for an hour and a half on Donphan, hopefully doing useful stuff. If you suddenly wake up in the middle of the night and realize you have a horrible mistake in your job script, you can wake up and delete the job rather than waiting until it finishes. So if you make mistakes, you can easily delete things and free up those resources again for other people. Again, very much recommended to try this hands-on. Now, another question we often get is, when will my job start? The best answer we can give is, we don't know ourselves. Unless you can predict the future, we can't tell you when your job will start. The reason for this is multifold. So first of all, like I already explained, the more resources you ask for, the longer your job will be waiting in the queue. But of course, also jobs usually finish earlier than they predicted. So if you ask for 10 hours, maybe it's done after half an hour, and that's fine. So we don't know what all the jobs are going to do. We also don't know what other people are going to do on the system, how many more jobs they will be submitting as your job is waiting in the queue. So everything is constantly balanced out across all the people, and you don't really know when your job is going to start. So you need to plan ahead and plan for the worst case. If you submit today, maybe it takes a week before it actually gets started. Hopefully you're not that unlucky, but it could happen. And you can game things a bit as well. You can look at the different clusters, see how busy they are, and maybe submit to a different cluster depending on how busy the others are. Or, and this is a bit of a hidden golden rule, is as long as you don't ask for more than a quarter of a node, your job will typically start quite quickly. 1 job, not 100. So on a cluster where 100 cores are available per node, if you ask for, let's say, 25 cores, or yeah, roughly a quarter, so 32, 16, 24, something like this, usually your job will start quite quickly. So if a quarter of a node is enough, try to stick to that or go lower. And just submit more jobs. So divide your workload into smaller parts. Of course, sometimes that's not possible and you need more resources, but that's okay. Yeah. Everything essentially. Yeah. It's a bit of let's say rule of thumb, right? There's no guarantees, but in practice, you notice if you don't ask for more of a quarter of a node, there's usually a gap somewhere on the system. You have like 100 nodes per cluster, and usually one of them is partially full and allows you to fill that gap. I've been explaining this for years, so many people know this rule, and the more people use it, yeah. I had a second question. Yeah. Mm-hmm. Yep. Yep. It's full. Yeah. 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 So yeah. First of all, we never know when that's going to happen. If it could be people within the default VO that consume a lot of resources, and all of a sudden, like you're being pushed down. But it could as well be that there's 10 free nodes on the cluster, and your job starts instantly without even waiting. So there's just bad luck, let's say. Now, you don't actually need an excuse to join a VO. If you say we're working, or even I'm the first person to use the HPC cluster in a research group, I want to start a VO, maybe because I need 100 gigabytes, the 25 is not enough, fine, we will not ask any questions. Now, there's already 150, 200 VOs, I don't know the number. 230? Yeah. Or 250 even, yeah. Responsible, yeah. Yep. And it's indeed a good reaction to join a VO to escape, let's say, the default VO. I think the default VO has half the people we have on the system. So as soon as a couple of people there get very active, everybody else in the default VO suffers. So to escape that, and the balance is sort of across VOs as well. We will have one huge VO and then many smaller VOs. So it's better to be in the second part. Yeah. Yeah. But yeah, very good question. And actually, the last week it was pretty bad for some people waiting in the queue because the big system was in maintenance as well. So everybody who was running on the big system moved to the tier 2, and things got horribly busy there. Yeah, but maybe people are preparing for papers, or yeah, you never know what's going to happen. There's so many people on the system that it's chaos, literally. Yeah. Okay. This is a very busy slide. I won't spend too much time on it, but this is a way to check how your job was doing after it has completed. So suppose you have a long job ID and you want to see how well was this job actually using the resources I was asking for. You can use slurm job info as a command on that job ID. It will give you this small report. And here you can see on which cluster it was running, which node it was running, or multiple nodes, maybe how many cores it was using. And it shows you when the job was submitted, when it was started, when it completed. So you can see how long it was waiting in the queue, how long it was running between start and end. And what's important here is it also shows you how much time was spent in terms of wall time. So between start and end, how much hours were in between, and how much CPU time was used. Now, in this case, it's actually really bad. Can somebody, well, it's actually on the slide, but why would it be really bad in this case? These things are almost equal. So it was running for, let's say, 8 hours, and it used 8 hours of CPU time, but we were using 8 cores. So this should actually be more like 64 hours if it was using all the cores all the time, using those 8 hours. That's not the case. So that probably means that this job was accidentally using only a single core. It was asking for 8, but the software was only using 1 core. So that's a waste of resources. So these type of things you should try to keep an eye out for. Now, what we typically tell people is when they figure out how many cores should I use, is you start small. Start with a small workload that uses 1 core, then try making it 2, 4, 8 cores and see if it becomes faster. If it doesn't become faster, you're doing something wrong in your job script, or your software just doesn't know how to use multiple cores. So don't ask for 1,000 cores and assume it will be 1,000 times faster by magic. Usually it's not, and you have to do some effort, or you need to tell the software correctly how to use the multiple cores. Also, this here is a sort of a warning sign. It was 82% of the time spent on those CPUs was doing actual calculations. 70 or 18% was system I/O, so moving data around and copying things like crazy, but not doing actual calculations. This is quite high. This should be single-digit percentage. So this is also a warning sign that something was wrong. And it's actually combined with the memory. You can see it was pretty much using all the memory. What was really happening here is that this software was intelligent enough to use all the memory available, but it actually had more data. So it was constantly moving data around to try and use the resources, but it couldn't because it was in a box with only 15 gigabytes of memory. So one solution here was to ask for more memory. Another solution is definitely to figure out why it's not using those multiple cores. So if you see these type of things, it's a bit of a warning sign that you have some homework to do. So if you add more cores, you expect things to become faster and to actually finish in less time than the 8 hours that you have here. Yeah. No, not necessarily. It's fine if it's a lot less. If you're very close to the limit, that's usually a warning sign that it's using everything it has, and the software may be able to use more memory if there would be more available. So this is already, it's not a strong warning sign. It may just be doing a good job of using everything that it has, but it does show you that it's like hitting a limit somehow. And then combined with the other warning signs, it tells you stuff. Yeah. As long as the memory is not the problem, it doesn't matter.
The amount of memory is also linked to the cores. So you might, if your software scales well with a lot of cores, but actually doesn't need a lot of memory, you still have all that memory available, even though you're not really using it. So memory is not as important as cores in that sense.
You can put slurm job info $PBS job ID in your job script at the end. And it will give you like this report. You won't see completed then because the job is still running, but you can like self-include this in the job script at the end. And it will give you some, this high-level report. It will not be 100% accurate, like the last minutes or so of the job will be missing. But yeah, it may be okay. And it could be good to always do this in your job scripts and just see how well it was doing at the time, and then try to learn from that as you. Right. This is another new slide that we added. It comes back to the overview that Lara showed of the CPU, right? The multi-core CPU, but it puts things more in context. So the gray box here is a full node with that multi-core CPU, actually 2 of them, 2 sockets. And then it shows you all the places where data can go. Now, this is important to know because where data is also determines how fast it can be accessed, read or written. So that's the next slide here. On the shared file systems, 3 different types, 2 different types of Scratch, or 4 in total. You can all put data there. Now, home is, don't use this for big data files. As soon as you hit a couple of 100 megabytes, it's not really well suited for home anymore because it's just way too slow. Job scripts is fine, that's kilobytes, but big data files don't belong there. VSC data is okay, but it's relatively slow. So if you're talking, let's say, tens of gigabytes, you should already be looking into moving your data somewhere else for the jobs to operate on. Scratch is fast and pretty big, and Arcanine is even faster, but more limited in terms of disk space. So in that sense, it gives you like a hierarchy of where data should go to access it in job scripts. Eventually, that data, those input files will land on the node as well. So the node also has a local disk where you can copy stuff to. That's where the tempdir path is for your job script. And then eventually your data will be loaded into memory and will be loaded in the cache of the processor as well. But that you don't really have a lot of control over. So all you can do is bring it close to the node or on the node, and then you start the software, and the software loads in memory, reads it, and does stuff with it. And then, of course, the software itself puts stuff in memory, eventually drops it to disk, and maybe you want to copy it out back to the shared file system, the reverse. So it's important to keep this in mind, like where stuff can be and how fast things can be. So this, summarized, your data is always stored on the shared file system, somewhere, home data or Scratch. When the software is running, it's on the processors, and the live data of the job, or at least part of it, is in the memory of the node. Usually, but the software itself takes care of that to load it there. Okay, and then there's one particular type of job which we call embarrassingly parallel. Not embarrassing because you're not supposed to use it, but it's trivial to split up this workload into many small parts. You each give them one core, and this can be hundreds of thousands or millions of these tiny tasks that you want to execute. Now, it would be very inefficient to submit 1 million jobs on the system. You actually can. Actually, 1 million is a limit that you'll probably start getting emails from us that we don't like you. But there's other ways of organizing this type of work. So you definitely can do 1 million small tasks. And there's some tools that help you with, like GNU Parallel is a good one, the worker tool, which is covered in our documentation as well. So if you have this type of thing where many small calculations that each take seconds or minutes and don't need a lot of resources, just know there's tools that can help you with doing this, and definitely don't manually submit 1 million jobs and never sleep again. That's not what you should do. Okay. Then Lara, we can cover some of the more software specific things.
So, I think it's on. So we already have a lot of software available. But what happens when it's not available? You can use Python virtual environments. Also with R, you can build on top of it. We've also now set up R that it's not filling your home dir anymore. So now it's also not messing with that anymore. So you can easily install also R packages on top. But for Python, we recommend that you use a Python virtual environment when you're trying to build something on top of it. You can, when you're making the environment and you want to build on top of some modules that are also already available, for instance, if it depends on NumPy, you load first the SciPy bundle, you create the new Python virtual environment, you source activate, and then pip install whatever you want in there. We've actually this is a process that actually has to make sure that it works everywhere. You have to repeat and repeat on all the clusters. So because of this, we've made also a tool to make it easier for you so that you don't have to maintain yourself all these different environments and have to update them everywhere if you switch from cluster to cluster. And that tool is called VSC-Vamp, which is installed on all the clusters. And so with that, you only need a module.txt file, which has all the modules that you want to depend on, and a requirement.txt file, which has all the Python packages that you want to build on top of it. And so you can run this in your job script. It will set up everything for you so that you then can run your Python code that needs these dependencies that are not installed there yet. So here is a quick overview of what it might look like if you want to install Beautiful Soup on the cluster. So you want the modules SciPy bundle and Pillow to be available in your Python virtual environment. And then with requirements.txt, you're building a newer Beautiful Soup. Beautiful Soup is already installed, but maybe you want the newest of the newest Beautiful Soup, and in the one available that's already installed is older, so you just build a newer one on top. What you do is you load the VSC vamp module. You use the following command, which is source VSC vamp activate. You point to the requirements.txt file and the modules.txt file. And then it's set up. So then you have a newer Python available. So as you can see, here's then a Python 3.13, which is newer than the OS one. And Pillow can be loaded, NumPy can be loaded, and Beautiful Soup can. So the caveats with installing software yourself sometimes is that you want software to be to perform as well as it can be. Also, to optimize the utilization of our clusters. So if you're using stuff like Conda, you're actually always not really running optimized software. You're using generic because Conda is made so that it can work anywhere and for everywhere. So it's very generic build. So it's going to be slower than when you're using an optimized build. This vast majority of the software that is centrally installed is optimized for the specific CPU clusters. And also when you're using Conda, you might break some stuff in your account. So it does a lot of stuff in your home directory and your bashrc. So if you're not that familiar with Linux, you can mess a lot of things up when you're using Conda and maybe not know your way out of it. Okay. So all the software installations we do ourselves here in our team, we do via EasyBuild. If you have a software that you would like to get installed and it's not there yet, and you want to make sure that it's the best good installation that will perform well on our systems, feel free to submit a request to us. Be patient though. Because you might have to wait sometimes. Really also plan ahead of this. Don't send us a week before you need the software request with like, I need this now, because we can, sometimes it will work out, but sometimes it will take us hours and hours to get something really done well. And so be patient with us. Sometimes it might take months to get something installed if it's really, really tricky. So we do everything with EasyBuild. EasyBuild was also originally developed here at the UGent, and it's now being used worldwide. If you want more information on EasyBuild or how to use it yourself, you can check the documentation. So another tool that we started developing here in UGent and also a bunch of other HPC sites in Europe is Easy, and it's a follow-up project to EasyBuild. And the general idea and the tagline is, what if you no longer had to install a broad range of scientific software from scratch on your laptop, on an HPC cluster in the cloud, and where anything you have to maintain yourself without compromising on performance. So EASY is a shared software stack. It stands for the European Environment for Scientific Software Installations. It's a shared repository of software installation. It provides a uniform way to access software, so you will have the same software environment on an HPC as on your laptop. It should work on any Linux distribution and any CPU. So we also have ARM and AMD Intel. It can work. It will work on your laptop, on your personal workstation, on an HPC cluster, or in the cloud. And it also supports a wide range of CPU and GPU architectures. And it's already available across like 50 plus systems across Europe. You can find in our documentation where they are. So what are the major goals of Easy? It's providing a truly uniform software stack so that you really know that you have the same software as anywhere. So it's also for reproducibility, can also be very valuable for scientific work. And also without sacrificing performance for mobility's sake. So it's an alternative to containers and Conda, which have their downfalls when you're focusing on mobility and reproducibility. We also started this project to avoid duplicate work because now we're already at HPC sites, we're already using automation tools like EasyBuild and Spec to get software easily installed. But still the HPC sites themselves have to do the actual installation, and you always run into some trouble sometimes. So this avoids that each HPC sites do that work, but they actually and skip to just relying on a central software stack with Easy. It can also be for HPC training and development of scientific software. So this is a little bit of overview of like the central software stack. So on the left, you have all the applications that are in Easy. And then on the right, you can see the different clusters. So you have Easy that actually streams to the different clusters, your personal laptop or cloud, where you then have access to the software. This is an overview of the software that is currently already provided in Easy. So we have GROMACS out there, we have TensorFlow, we have PyTorch and a Wharf. So a bunch of, a wide range of tools that are used by scientists on HPC sites. So at the moment we have over 700 different software packages for all those different CPU targets. We also have a number of tool chains in there from 2023A to 2025, separated over 2 Easy versions. And you can also find a detailed overview of all the software that is available in our documentation if you click on the link below. Using Easy should also be very easy. So the first thing when you're on a system, which will work here at UGent, is you do an ls cvmf software.io, and this will try to connect to the to the CERN VMFS server. And if that step returns, yes, I am there, and it exists, that directory exists, then you can source the init script and you can start using Easy. Once you have stored the init script, all the modules that are available in Easy can be loaded. So this is similar like how you load modules on this, that are also centrally installed here at UGent. Once the module is loaded, you can start running. And so you can even install Easy on your CERN VMFS on your Raspberry Pi, make Easy available, and start running GROMACS on there without having to install anything. You can also use it on Windows and Mac OS with virtualization, and we also have documentation on this. Here is a small demo of, for instance, LAMP that is also available on our cluster. So if you would like to try using Easy, you can try the script later today. So on which systems is Easy available? So at the VSC systems, it's now already available at UGent, VUB, and also TO1 Hortense. And what is missing? It's also now available at KU Leuven, I think. Yeah, so KU Leuven, it's also available now yet. So the only site that it doesn't have it yet at VSC is in Antwerp. So all the other sites have it. And you can, of course, also use it on our cloud if you install CERN VMFS. In 5 minutes, all the software that is in there becomes available to you. Then on a new European level, it's also on a number of your HPC GAU systems now, and it's also, it's also at other European systems such as Snellius in the Netherlands, the University of Stuttgart, but also in Groningen, and a bunch of other things. And then it's also integrated in the European Open Science Cloud, so you can easily spin up a virtual machine in the EOSC with Easy already available when you're when it started. And an overview you can find in our documentation of everything. So I'm gonna leave it back to Kenneth.
Okay, so we're ready to wrap up now. This whole section about scientific software, loading modules, virtual environments, easy build, easy, that's a lot to digest. And just last year, we did a VSC training. So together with the other Flemish universities, we organized a training on getting your software installed. So which tools can you use? What are the downsides, pros and cons of each of these tools? What's interesting to use for which type of software or which type of use case? So this was an in-person training last November, which was fully recorded. So you can find the link to the recordings through that link there via Centrum/GSSI training. And we covered many of the topics that we've covered here as well, but also additional ones like using containers, building container images, more in depth on using Conda and the caveats there that you need to take into account on an HPC system. Some stuff on installing R packages and Julia packages as well. And then also a general overview of what to take into account or what to be aware of with each of these tools. So all of this was recorded. The slides are available as well. So if this is something you're struggling with, I highly recommend taking a look at all of this and see if it helps you. We're planning to organize this session again in fall of this year, probably October, I think. But we need to finalize the date for that and make sure it all works out. It's probably going to be in person again in Brussels. And we do intend to record things again if possible. Of course, for any questions related to all of this, you can always contact the HPC support team as well. And that's to wrap up with. So if you have any questions beyond today, so of course you can still raise questions, and especially during the hands-on, we will be running around and helping you out as much as you can. But you can always contact us through hpc@ugent.be, and that's the main way of contacting us. So don't contact us personally via email. Don't send us messages in Teams because we will never do anything else than answer chat messages if we start doing this with 5,000 plus accounts. So the email address is really the main way to contact us. There's essentially 4 or 5 people that keep an eye on this all the time. And if needed, we move support tickets from one person to another if necessary, if people go on leave, or if it becomes too technical or somebody is an expert on a particular thing, we move things around within the team as well. You should also help us help you. So don't say, I have a problem and send the email, but give us some details. What are you trying to do? Which job script are you trying to use? What errors are you seeing? What have you tried yourself? Maybe you've asked ChatGPT and it gave you some instructions. Feel free to share this with us. It's not a stupid thing to do because these AI tools are actually can be quite useful in the Linux environment. Linux is everywhere essentially. So it is quite possible that you get some decent help from these tools. But if you're stuck, ask us and just give us as much as context as possible. Definitely job IDs are very relevant as well, because then we can easily trace what was happening with your job and why it didn't work the way you expected to. And again, here, like Lara already mentioned, you'll have to be a bit patient. You can imagine with 5,000 plus accounts and many people active on the system on a weekly or monthly basis, we get a lot of questions. So you can see the ramp up there in terms of number of support tickets that we have been getting over the last couple of years. The last year is missing, but there we broke the line of 3,000 tickets in a single year. So we are 4 or 5 people helping each other out to answer them, but you may need to wait a while until you get a good answer. And sometimes we need to just check internally as well to formulate a good answer or to figure out the problem ourselves before we can answer your question. But again, don't let this hold you back to actually raise questions. One final thing, on the recent VSC user day, so not last year, but the year before, there was a session called HPC Best Practices and Some Magic Tricks, which our colleagues from the VUB and Leuven presented. This was recorded as well, and the slides are available. If you're feeling you're going beyond the basics, I definitely recommend taking a look at this as well, because there are some interesting things there that can help you quite a bit in working more efficiently or getting your jobs to run faster. So all the links are in the slides. And then we're ready to wrap up. Time-wise, we're doing quite okay. Oh, exactly 12 actually. So I think we're ready to have a sandwich lunch. We can take a couple more questions, yeah, if people want to. So go ahead. Yeah. So what type of volume of data are we talking about? Is it gigabytes, hundreds of gigabytes? Okay. It depends then. I mean, it also depends on how frequently you need to download those files and how many there are. Is it 10? Is it 1,000? That all matters. It also depends on what you need to download it to. Is it a Linux system? Is it a Mac system? Is it a Windows system? Yeah. From Linux to Linux. Then I would recommend looking at rsync. So rsync is a command line tool that you can say, I have a remote server. There's a directory in there. I want to sync this data with my own local system. I just run rsync and it checks what has already been copied or what has changed or what it needs to copy over. If that transfer gets interrupted, it can just resume by trying again. So any partial copies, it will not do again, essentially. So rsync is quite good at that. I think this is also covered in our documentation. It may be a bit basic there, but just ask ChatGPT for rsync help and options to use. It can compress things. It can do parallel streams to make copies faster. But that's definitely the tool you should look at. Yeah. Yep. Yes. Yeah. So let me go back to the slides for some context. So these files, right? These .o and .e files. Yeah. So when your job is running, while it is running, you will see the .o and .e files already being created. There may be some output in there while the job is running, but things are also buffered. So while the job is running, it may actually stay on the node for a while until there is enough data, and then it's flushed into the file, and you can expect how things are going. So don't expect live updates to see there. But if it generates enough data, let's say a couple of lines every couple of minutes or something, you will be able to see how things have been going while the job is still running. Yeah. So yeah, as soon as your job is starting, these files will be created and you can just inspect them live on the system. Of course, then you shouldn't edit the file while the job is running because then God knows what will happen. Yeah. But yeah, you can. That's a good question as well. Any more questions? Yep. Technically, yes, but it depends a lot on the details. How accessible is that database? Is it accessible from the system to wherever the database is running? There may be a network connection issue that we can fix. We can open up access to the system. Maybe the database system needs to allow incoming access from our supercomputer. And what you do need to be careful with, it's very easy to submit thousands of jobs that all start talking to this database, and it will bring it to its knees. Right? So that's something you have to take into account. If you're the only one using that particular database and you're only going to submit a couple of jobs at a time, that's probably fine. But the step from there to thousands is trivial. And that may kill the database or make it suffer. Yeah. But technically, it is possible. The specifics there matter a lot. So that's a great one to open a question on. So send an email to HPC UGent. Give us the specifics. Also, what you want to do typically, is it just storing numbers in the database or are you streaming lots of data to it? That all matters. Yeah. There is a question in Teams as well, which I'll answer here. Can you use EasyBuild yourself to install software in your account? Yes, you can. EasyBuild doesn't need any special permissions. It just runs as a regular user. And all it needs is access to a directory to save the installations in, essentially. So if you have some directory that you can access, you can use it. The next question is then, where should things go? A good question. It depends a lot on how much software you're installing. So if it's like a single installation that you'll be using over a long time, and it's not a big installation in terms of number of files or how big it is, you could put it in your data folder. If it's lots of stuff with many small files, maybe Scratch is better. Yeah, and I think that's a good answer to that. So you want to have it in either data or Scratch, probably not your home directory, which is too small and too slow.